Alright, recall that in the previous lecture we learned how to visualize a differential equation as a direction field. Right, so given a differential equation, we construct a vector field whose first component is 1 and whose second component is exactly the same as the right hand side of the differential equation. Then the reason why it is such a great tool to visualize differential equations is because the differential equation tells us that the direction field is tangent to every solution at every point. So which basically means that if you want to plot solutions on top of the vector field, then you kind of need to follow the arrow. So it's going to be something like this. So if you want to plot a solution. Also, last week we learned that there are two different approaches to visualize it. So basically we can make all the arrows have the same x component, which is the left plot. Or we can make all the arrows to be of the same magnitude, which is the right plot. And usually this is more convenient, well, in my experience. So there are very, very few exceptions. So basically, it's most of the time we're going to use the second approach. So when all the arrows have the same magnitude rather than this. All right. Although there is no general method that allows us to just look at the vector field and figure out whether it comes from a separable equation or not. But still, sometimes it is possible. So the simplest case probably is that when our equation does not have an explicit y in the right-hand side, so which means there is just a t in the right-hand side. So the differential equation tells us that the derivative of the unknown function is the given expression in t. Well, but if the direction field does not have y in the right-hand side, it means that changing fixing t and changing y, we do not change the right-hand side. So you can easily see it from the picture. So for example, I don't know, if you look at all these arrows along this whole vertical line, t equals 2, it's the same, but y changes. But at the same time, changing y shouldn't change the right-hand side of the differential equation. So which means that all the arrows along this line are exactly the same. Or if you want another example, say here it's about 3.5, I think. So along all this line, all the arrows are the same, are equal to each other. Or I don't know. So here t equals 4. So along the line t equals 4, all the arrows are equal to each other. And of course, this kind of behavior can be immediately seen from the direction field. So in other words, suppose that you didn't know the differential equation. So if you just look at the vector field, what you see immediately that along every vertical line, all the arrows are the same. So which means that the right-hand side of our differential equation does not have a y in it, so it only has an x, right? So, but just looking at this, you can immediately see that our differential equation looks like dy dt is some expression g of t. It doesn't have y. And of course, in the same way, since well, if the right-hand side of our differential equation does not have a t, then instead along every horizontal line, for example here, if you look at this line, y equals 1.5, I guess, all the arrows are equal to each other, or along the line y equals 4, all the arrows are equal to each other, and so on. So along every horizontal line, all the arrows are equal to each other. So it means that again, even if we don't know the original differential equation, at least from the vector field, we can immediately see that the right hand side does not have a t. It is only a function of y. So for instance, of course, it means that the equation is separable. These equations have a special name. They're called autonomous equations. So when the right hand side does not depend on t. And again, what is special about them is that the direction field is invariant under horizontal translations. So which means that if you take any solution and if you move it to the left or to the right, then you get another solution of the differential equation.